I'm Professor Chun-Chen. I will be substituting for Dr. Schmid this week. And this is Physics 3C, right?
Yes.
Yes, all right. So instead of using the projector, I think I'm going to use a blackboard. And if you cannot see it, please sit closer to the front or just raise your hand and shout and let me know. So I think the last topics for chapter 33 is magnifying glass. That's what we'll be going over today. Can people see my handwriting? Yes. Good. So what does a magnifying glass do? What is its purpose? Enlarge the image, meaning let the object get closer to the near point, which is, what's the near point, the distance? For normal eyes, 25 centimeters. Yeah? All right, so first of all, let's remind ourselves, if I have a closer object, it will make bigger retina image. And the way to see it, so suppose this is your eyes. And this is where the object is. So the object will form an image on the retina, correct? This is not a perfect picture, but you all have the picture in your book. But it's always good to just try to draw the picture with your hands. So this will be the image. And what this picture is telling us is that if this angular extension is larger, then the image that is formed would be larger or smaller? Would be larger, right? Because the way to think about it is, if I move this object further away, the image becomes larger or smaller from your experience? Smaller. And what is the angular extension? Larger or smaller? Smaller, right? So this is telling us is that in order to tell us how big the object get magnified, one crucial quantity is this angular extension. Does everybody agree with this? Yes. Yeah? All right. So let me All right, so again, the magnifying glasses let us get closer to the object than the near point, which is 25 centimeter for normal human eyes. And therefore, this will result a bigger image, as we just argued. Yeah. All right, so suppose you have a magnifying glass, which is sitting right here, and this is your eyes. And here's my object, say a leaf. And the location of the object is just inside the focal length of the magnifying glass. Then where does the image form? You'll be to the right or to the left of the object? To the left, right? So all you do is to extend these two rays all the way up. And that's where the image is. So this is your object, and that's your image. And let's suppose the object has a height of h, all right? And the distance between the objects and the length this is the object where the distance between the image, and the length. This is the image. And the reason why I want to define these distances is the fact that you already encountered the length equation. Right? So I want to define the various distances first. All right, so this angle here, let's call it theta prime. All right? So here, first of all, this length, this magnifying glass, it is a convergent length. Yes? So what type of image does it make? Is it a real image or is it a virtual image? Virtual, right? Because you have to extend this line, and that's where you get the image. Say it again? Can you please repeat that? Right, so this is a virtual image. Oh. Everybody agree with this? Yeah? And in order for the eyes to focus, this image must be at least 25 centimeters away from the eyes. And suppose your eyes are relaxed, then where does the image form? There will be infinity. All right, but without the magnifying glass, we also have a relation where this angular extension, theta, is given by the height of the objects divided by the near point, distance n, which is 25 centimeters for normal eyes. So how do you define the magnifying power of a magnifying glass? All you have to do is to compare theta prime with theta in the case without a magnifying glass. That would tell us the magnifying power of a particular magnifying glass. Everybody agree with this? Yeah? All right, so with this geometry we have on the board, we can rewrite this to angles in terms of the distances, right? So suppose the angles are small, then we can make use of the small angle approximation, which tells us that the angle written in radians is equal to sine of this angle or tangent of this angle. Correct? Good. All right, so what is theta prime? So for relaxed eyes, the image should be formed at infinity. And the object would then be located at the focal point of the length. So that tells us that theta prime is equal to h over d0 or f0. Where f is the focal length of this magnifying glass. And how about theta? Again, from small angle approximation, we know theta. This is roughly sine of theta, which is roughly tangent of theta, right? And theta is written in radians. Have you seen this before? Yes or no? You have to be more responsive, otherwise just all fall asleep. All right, so what is tangent theta? How do you, here I have a triangle, right? So it will be opposite over this. Everybody agree? Yes, good, very good. So you are responsive. That's a right angle there. So tangent will be this divided by that. So that tells us theta is h divided by n. So far so good? Good. All right, so h and h can cancel. In the end, this will give you just n divided by f. Any questions about this? So of course, there's some way to increase the angular magnification of the magnifying glass. And the way to do it is to place it closer to your eyes. So if the eyes is, let's see, focused to the near point, that tells us the image will be at minus n. Right, d sub I will be at minus n. And this happens when the magnifying glass is very close to your eyes. So then we can make use of the lens equation. Which tells us 1 over d0 plus 1 over di is equal to 1 over f, which is the focal point of the lens. So let me do it step by step. Right, this is a general equation. And now we know the image is formed. It is a virtual image. It is formed at distance at the near point. So that tells us d sub I is equal to minus n. Everybody agree with this? Yeah. All right. So I'm going to do a trick by moving this term to the right. And given that d sub I is minus n, I can just substitute it in, and minus minus become a plus. This is the relation. This is just simple algebra, right? So now once again, we can go ahead and calculate the angular magnification for this particular case when the magnifying glass is very close to your eye. So again, theta prime is h over d0, and theta is h over n. This is the near point. So h cancels h again. And now I'm going to rewrite 1 over d0 in terms of the focal point f, focal length f, as well as d sub I, or n, sorry. So let me just give you the final result here. So again, all I did was nothing but making use of the length equation and rewrite various quantities for the angular magnification in terms of the this near point distance, 25 centimeters, as well as the focal length of the magnifying glass. So is this bigger or smaller compared to this case? It's bigger, right? All right, so suppose I'm making use of a convergent length whose focal length is 8 centimeter. And this is actually the type of lenses get used by the jeweler. So estimate what is the magnification when the eyes are relaxed. And second part, what is the magnification when the eyes are focused at the near point? Which are the two cases we just discussed, right? So what is the magnification for the first case when the eye is relaxed? Which formula to use? N over F. And do you know what N is? What is N? 25 centimeters. And what is F? 8, right? So that's simple. How about the second part? Same thing plus 1. All right, so you are all expert now. So of course, magnifying glasses find a lot of applications in our daily life. And one very well-known application is a telescope. Have you all seen through the telescope? Yes. Watching the stars? No? All right, so the older version, or a very traditional version of the telescope consists of how many lenses? 2. One is the objective lens, and the other is the eyepiece, right? That's basically, I mean, if you just take randomly a telescope from the store, that's what it looks like. So it consists of two convergent lenses. And that's your eyes. So on the far side, the lens is called the objective lens, where between the objective lens and the eye, there's the eyepiece. So what does the objective lens do? Where is the star? Which side? There will be a far distance on the left, right? So some distance objects would emit light rays from this side, and given that the object is very far away, these light rays look like parallel. Yes? All right, so what the objective lens does is that it makes an image of this distance object at its focal plane. Which part?
The middle.
Here? This is the image formed by the objective lens. Yes? So here, let's see. Let's call this point F0. So this is the first image. So once again, you have objects at distance, so that there are parallel light rays from the object at infinity, and after these rays pass through the objective lens, there's the first image that is formed at the focal plane of the first lens, which is inverted. Right? Any questions about this? So far, so good? All right. And then, all right, so let me just write this down. So the objective lens So once again, the objective lens makes the image of a distant object at distant objects at its focal plane, which I call I1. That's your first image. And then this image is viewed through the eyepiece. Right? Just think about your telescope. Right? So you view this image through the eyepiece, and how does the image look like? Does it get magnified or not? Does the image viewed through the eyepiece get magnified? Sorry, that's T. Yes or no? Yes. All right, so this image is viewed through the eyepiece. Again, you have much better picture in the book, but just want to illustrate the point here. So where does the image form? Can anybody see the purple lines? Yes? All right, so the slide rate continues. At the eyepiece? How does this rays go? They all converge into your eyes, right? So you have to extend this rays. Oh, sorry, I'm actually drawing it incorrectly. No, you are right. I'm sorry. They're actually going out, diverge. Sorry. So where does the image form? Do you have to extend all this rays all the way down? So this will be the final image.
So where does the image form?
Here. So this is the image view, yes, through the eyepiece.
Does it also have to be behind the objective lens?
No, it depends on the configuration. You mean, are you asking whether the image is always on the side?
Mm-hmm. Yeah.
There will be some conditions that have to be satisfied.
Okay.
But you agree with this configuration I just draw? That's where the image should be. Correct? All right. So let's now define some distance so that we can write down relations or equations to relate various distances. All right, so this distance here this is the focal length of your objective lens. So I'm going to denote it as F0. Everybody, is this clear what F0 is? This is the focal length of the objective lens, and that's where the location of the first image is, right? Where the focal length of the eyepiece, let's call it F sub I, and of course, the corresponding this would be the focal point of the eyepiece. So what that means is, in order to magnify the second image, that get back to the question just came from this slide, in order to have the second image magnified, you need the first image, which is just inside the focal length of your eyepiece. Right, this is how we started today's lecture, when we look at just one single magnifying glass. All right, so, and let's define some more variable. And one important one is this angle theta. Because once again, in order to find out the magnification, angular magnification, I need to know this angle theta. And let's call this angle theta prime. All right? So suppose if there's no magnifying glass, you just view the object through the naked eye, then this angle theta would be the same as the telescope angle. Where from the geometry, we know theta is h over the focal length of the objective lens. So how are we going to define the magnification in this case? Given that theta is the same, this angle theta is the same as the naked eye angle theta, there will be your normalization. In other words, in order to see how big this final image get magnified, I have to compare angle theta prime to theta. Right? This is like before. So that's what we try to find out. The ratio of theta prime to theta. What is theta prime? Say it again. Is it? So theta is the ratio of the object height to f naught, the focal length of the objective lens, where theta prime is h divided by the focal length of the eyepiece. Sorry, this should be f sub e, meaning the focal length of the eyepiece. So in the end, once again, h cancels h, and the magnification is given by the ratio of the focal lenses of these two lenses, meaning f naught divided by fe. The focal length of the objective lens to the focal length of the eyepiece. And is the image inverted or upright? You can see, right? Upright or inverted? The final image. Inverted. That's a big purple one on the far left. So to signify that fact, we just add a negative sign to remind ourselves the final image is magnified and it is inverted. You agree it's inverted, right? Yes. All right. First, of course, there's some way to make the final image to be upright, and you need to change the lens configuration. I mean, this lens configuration always give you the inverted image. So there are two ways in practice. One is called the Galilean telescope, which instead of making use of two convergent lenses, this Galilean telescope make use of one convergent lens and one divergent lens. So this is a configuration. You have a convergent lens, where this is, again, the objective lens, where the eyepiece, in this case, is a divergent lens. And again, you can try to draw the light rays and convince yourself, in the end, the final image is upright. And actually, let's see. All right, so this is the, yes, the top one, this is the Galilean telescope, where once again the parallel rays from distant object coming in and going through the objective lens, and therefore the rays are convergent. But once the rays go through the second piece, namely the eyepiece, which in this case is a divergent lens, the rays would go in a different way than the first telescope we discussed earlier. So now in this case, the image will be formed right here. Any questions about this? Right, so I think, once again, this is a very good practice for you to go home and try to draw the rays and convince yourself in the end the image will be upright. All right, but so, good. So the second way to make the image upright is called the spyglass design, where instead of two convergent lenses, the spyglass has three convergent lenses. All right, so in this figure, you see the configuration. You cannot see it? Okay, let me try. Is this good? All right, so this is the initial parallel rays coming in, and then they form the first image right here at the focal length of the objective lens. And then the rays go through, let's see, the third lens you add between the objective lens and the eyepiece. All right, so the final image is right here. Again, this is upright. Any questions about this? This is good? All right. Okay, so one example. The largest optical reflecting telescope in the world is located somewhere in Wisconsin, and it is roughly 1 meter in diameter. Yes, it's 102 centimeters. It has a focal length of 19 meters, and the eyepiece has a focal length of 10 centimeters. So what is the total magnifying power of this telescope? You have the answer there, but how does the answer come about? Remember this formula we derived earlier, was this case just has two convergent lenses. The magnifying power is given by the ratio of the focal length of your objective lens to the focal length of the eyepiece. Right? So that's the first part. What is the length of the telescope? Now the answer is blocked. You just go back to this figure. Right? What would be the length of the telescope? Make an estimate. It will be this distance plus this distance, right? And plus this distance again. Yes? So suppose the eye is relaxed. Then what that means is this first image has to be at the focal length of the eyepiece. Everybody agree with this statement? Right, so once again, if the eye is relaxed, then this first image has to be at the focal length of the eyepiece. So what that is telling you is that for relaxed eye, this is your first image, I1. This distance is f0, which is the focal length of the objective lens. This is f sub e, which is the focal length of your eyepiece. So what is the distance between the two lenses? I already drew this for you. F0 plus Fe, right? But then, of course, you have to take into account the fact that there's also a distance between the eyepiece and your eye. So this is Fe. So the distance, or the length of your telescope, would be 19 centimeter, which is F0 plus twice Fe. Yeah?
Would the magnification equation work for Galileo's telescope?
No. You have to like rederive it.
Okay.
All right. Okay, so I think probably this is a good place to stop.